Okay, so picture this. You've got to take the pulse of something 2 miles underground. It's hotter than boiling water, and it's under so much pressure it could literally crush a submarine. So how in the world do you do that? Well, that's the engineering challenge we're going to dig into today, how we listen to the secrets of an oil and gas well.
So let's just dive right in. Imagine you've just spent millions, sometimes hundreds of millions of dollars, drilling a hole miles into the earth. What's next? How do you actually figure out what you've got down there? How do you take its pulse, check its health, and figure out what its future looks like?
And look, this isn't just some academic question. The answers to this, they literally determine the fate of that massive investment. Is this well a gusher or a total dud? Is it even safe to operate? Do you pour millions more into it, or do you just cut your losses and walk away? Getting this diagnosis right is, well, it's everything.
So how do you start to answer that billion-dollar question? Well, you might be surprised to learn that the first step in this deep earth diagnosis, it doesn't happen miles underground at all. Nope, it starts right up here, on the surface, with the equipment you can actually see and touch.
Think of it like this. It's kind of like a doctor checking a patient's vital signs, right? Before you do any invasive tests, you check the basics. You take their temperature, check their blood pressure, see what's going on. This first layer of diagnostics is all about reading the well's surface vitals.
So what does that actually look like in practice? Well, it's a journey, and modern systems use this whole network of computerized sensors to track everything. First up, the fluid comes out of the well and hits the flowhead. That's where we get our first pressure and temperature readings. From there, it gets wrangled through something called a choke manifold, which is basically a bunch of valves that control the flow. We measure conditions on both sides of that. Then it's off to the separator, a super important stop we'll come back to in a sec. And finally, we're monitoring the tanks and burners for our last measurements. Every single point gives us another piece of the puzzle.
Okay, so that separator I mentioned, that thing is the absolute heart of the surface operation. Its one and only job is to take this messy mixture of stuff coming up from the well and carefully split it apart into its main components: oil, gas, and water. This is huge because it lets us measure and analyze each one of them all on their own. It's our first real look at what we're dealing with.
And you would not believe the amount of information we get right here. The separator tells us the exact flow rates for the oil, the gas, and the water. It clues us in on the gas composition, like are there dangerous gases like H2S in there? It measures stuff like sediment and water content, and even these really complex properties like how much the oil might shrink as the pressure and temperature changes. It's just a staggering amount of data, all gathered right there on the surface.
But here's the catch. Everything we've learned so far, it's just a symptom. It's what the well is showing us on the outside. To really understand the why, to get to the root of the problem and make a truly accurate diagnosis, we have to go deeper, way deeper. That's where the most important clues are hiding, thousands and thousands of feet below.
And this is where things get really interesting. To figure this out, we need eyes in the deep. We have to send these incredibly advanced sensors way down the wellbore, right into an unbelievably hostile environment. This is the second, and you could argue, the most critical part of the whole diagnostic process.
And when I say hostile, I am not kidding. These downhole gauges are absolute marvels of engineering. I mean, they have to survive scorching temperatures, pressures that would crush most things, and even the violent physical shock from tools like perforating guns. And a perforating gun is basically what it sounds like. It's an explosive charge that blasts holes through the steel well casing so the oil and gas can flow in. It's just a brutal environment, and these instruments have to work perfectly in it.
Now, because those conditions can be so different from well to well, you can't just use a one-size-fits-all sensor. Engineers have to pick the right tool for the job. You can think of it like choosing between a delicate surgeon's scalpel and a rugged sledgehammer. For tests that need insane precision for later analysis, they'll use a high-accuracy quartz gauge, that's the scalpel. But for just surviving a really nasty operation, they'll go for a tougher sapphire or strain gauge that's all about durability. That's your sledgehammer. It's always this trade-off between getting perfect data and just making sure the tool survives.
Okay, so you've picked your tool, and now you've got this amazing, rugged sensor deep inside the well, and it's collecting all this priceless data. The next huge question is, how do you get that information back? Do you want it right now, or can you afford to wait and get it later?
Turns out there are two main ways to do it. On one hand, you have downhole recording. This is basically a time capsule. The whole unit, the sensor, the battery, the memory, it's all self-contained. It just sits down there recording everything. And you only get that data once you pull the entire tool back out of the hole. On the other hand, you have surface readout. This is your live feed. The sensor is actually connected to the surface with a special electric line, sending data back in real time. So the engineers can sit there and watch what's happening as it's happening.
Now, you might be thinking that time capsule method sounds a little old school compared to a live feed, right? But honestly, it's often more than enough. The reality is, even though these recording gauges are limited by their battery life and their memory, the modern ones are perfectly capable of handling most standard testing operations. They're really the reliable workhorses of the industry.
So, at this point, we've got our two big streams of information. We have the vital signs from the surface, and we have the deep internal readings from down in the well. The final step, of course, is to put all of those pieces together and assemble the complete puzzle.
And this, right here, is the key takeaway. The surface data tells you what is coming out of the well, but the downhole data, that tells you why. Is the pressure dropping? Is one part of the reservoir producing more than another? You need both to get the full story. You have to move from just observing a symptom to actually understanding the diagnosis. And together, they create that complete picture that lets engineers make those billion-dollar decisions with real confidence.
It's really just incredible technology, isn't it? All of it built just to listen to the faintest whispers from miles underground. And it leaves me with this one final thought. If we've developed these amazingly sophisticated tools to take the pulse of a single well, what could we learn if we started using that same mindset to listen to the pulse of the entire planet? I'd love to know what you think.